Hello YouTube, iFixItAll here, Team iFixItAll. What is a relay? A relay is nothing more than a switch. Oops. Once upon a time, someone needed to create work done by making and breaking contacts. Contacts are, simply put, like what's on your wall, a light switch. That is a mechanical on-off switch. There's different kinds of switches, like this one. Dang it, turn that light on. Momentary, mechanical, that allows electricity to travel through here and out to supply power to something else and have its own ground, independent ground wire and what have you. You could have a, that doesn't belong in there, that's the relays. And that's a, yeah, that's a relay as well. There's momentary. Here's a selector switch. And if I snip with my flush cuts here, a zip tie, this is a selector switch. The main power feed would come in, and it's physically bonded. Only to the pivot rivet right there. That would make this wire the common. Power would travel through this rivet, which is fastened to this brassish copper high quality contact, and I could select power to go out to a device connected to the blue, the black, the white, yellow, or gray. Selector switch. I could have a rotary switch, which means there's commons here, or a common, and depending on which you could solder wires to these guys and send power out somewhere to do work. Rotary switch, so we got momentary, selector, rotary, push button, momentary, we have a slider, with the slider all the way this way, that would bridge this contact to this contact. So I could come in here, I selected this position, so that would allow power to travel from here and jump the gap to go out to do something. I could have circuit board mounted little dip switches here, which I thought I had one of these down already. Oh, got to peel the cover off. So peel this little protective cover off. Get off me. So this is just 1, 2, 3, 4, 5, 6. 6 switches in one dip dual inline package where you can select by moving the, here are the little clicks. Now these are usually used in circuit boards to binarily address something. 1, 2, 4, 8, 16, 32. You could assign a binary address to something. Let's say that if something's hooked up to this entire chip is wired to another circuit chip that's adjusted to be a 0. Make sure that's 0, 1, 0, 0, 0, 0. Let me make sure all those are down. Yeah, so this would be binary 16. Because it's 1, 2, 4, 8, 16. Because the circuit chip would be seeing that the rest of the pins are getting binary zeros, lows, so that would be binary 16. And that is 1, 2, 4, 8. 8 plus 4 is 8 plus 4 is 12. And then 2 more is 14. And then 1 more is 15. 8421. So there's that. Put this plug on the end here so I don't lose another one. The topic is, what is a relay? I know, I'm getting there. It's going to be a minute. There is a rotary switch, which is very similar to a selector switch. This probably came out of a fan of some sort. Momentary again. There's a selector switch we all might be familiar with. Again, it's just going to power on, power off. So we've got another switch here, another kind. It's a rotary switch, which you just use a little screwdriver and you can select You could have several of these and address a circuit board or a device through Modbus or CAN bus or what have you. So we'll put the switches back because switches were probably the first thing that was necessary in the world of controls and electrical controls and what have you, before we migrated to something called a vacuum tube, which overseas they call them valves. Vacuum tube. I don't know what kind of tube this is, but I need to find a home for it. Somebody's out there who needs one for an old radio or a communications device. Vacuum tubes were second to come around before your basic switches. There's lots of different kinds of switches out there. This is a type of a switch. It's a solenoid. A solenoid is like a device when you hit your power door locks. A solenoid usually is, that terminology is used when it's applied to a situation where there's some heavy lifting involved, or there's some real major work transition involved. A solenoid would be connected to a metal rod that could move a linkage to unlock your doors. But for conversation's sake, solenoids and relays share a common denominator. They all have what they call coils inside of them. So let me get set up and I'll show you all that. Hang tight. Relays serve a purpose in the fact that it automates things, because instead of having people sitting around working a switch manually to get telecommunications done or electricity delivered to certain places, you can control a relay. This is about the most basic relay you can come across right here. And here's what's going on. I got me a pointer here. Either DC or AC powered. These things can be either. You have to read the documentation if you want to play around with this stuff. This relay tells us that it is what am I doing? Hang on. There it is. In the upper right hand corner. Focus. 12 volt. Now what's really interesting is it doesn't tell, yeah it does, it gives us the symbol for a battery. Let's see if we can zoom in on that. That is the symbol for battery. If it was AC, it would have a sine wave like that, or it would just say AC, kind of like this relay here. Let me open it up. Its specifications tells us it's 120 volts AC, and it's rated up to 10 amps. You have to read these things. So the automation part of the switch comes in where the coil is. This is a coil. And this little human interface, little metal sticky out part, is what you would connect wires to. Now, this camera is not really doing us any justice. That pin right there begins the run of that little thin wire. Let's see if we can see it. Let me first locate it. There it is. If you can't see it, I'm sorry. It's a little thin wire that comes off of here and jumps to this plastic post, wraps around this thing like 600 gazillion times, and then comes back over to this post. That itty bitty thin wire you can barely see right there. And I don't even know how thick that is. It's, gosh, when we're talking about human hairs, it's probably, gosh, I wouldn't even know what thickness that is. So the science behind this coil is a wire comes in here, goes around in a circle, and it's a plastic post, but there's probably going to be an iron or steel core, which we can see right here. Ignore this metal tab for a minute. We're not going to get there. And it wraps around all the way up this, and it does that. I would speculate this one wire here is probably 100 feet long. I took the resistance reading on it, and it's about 580 ohms. And I don't know what gauge wire it is. But it is really, really, really thin wire. And the science behind this is when you take a conductor and you run it around in circles around an iron object, which our iron object happens to be right, again, ignore this. Ignore this metal flat piece of steel. We're looking right in here. There's an iron core that travels full length of this. And it just it's just sitting in there. It's not electrically touching this wire at all. It's just that iron core is dropped into a hole in the plastic, and then the wires wrapped around the plastic. The science behind this is that when you bring electricity into a scenario where it has to go around in circles surrounding an iron core, a magnetic field is created like on the Earth. You have a, let's just say for conversation's sake, a North Pole and a South Pole. And it has a magnetic field that goes around this way, everywhere. I don't even want to get into the science of magnetic fields, but it creates a magnetic field. And as a result, since this little tab is magnetic, because it's steel, it gets sucked down. As a result of it getting sucked down, it is mechanically attached to this doohickey over here. And then it makes contact. Notice this mechanical doohickey here transitions to plastic which is made in such a way that its only job is to move this contact over. This means that this part here is the contact side, and this must be the common. Usually your stationary object, your stationary set of contacts is the common. And right now it's in an open state, so we call this a normally open relay. Let's see if we can even get it to zoom. There we go. And I'm going to make the switch myself. Again, this wiring begins down here and comes out over here. So you could energize this with 12 volt positive here and give it a ground. It'll create the necessary magnetic field to mechanically suck this contact down, or suck this little mechanical arm down, because of magnetism is created. You create magnetism by running electricity into circles around a ferrous object. You create magnetism by doing that. And now you put that magnetism to work. The magnetic field moves this down and gives you your contact. And all right, so as a result, we can identify by staring at this for a little while that these two pins on the relay here are not in any way electrically affiliated with this electricity coming into the coil. Affiliated meaning they're electrically isolated from one another. That's another benefit of a relay. There's a lot of benefits to using relays, but normally if you're questioning a relay as like, what is the coil side of the relay and where are the contacts side? A lot of times, if your coil has smaller input pins, we classify that as the low current side of the relay. Low current side. It draws very little energy to create the necessary magnetic field to close this contact. Now over here we call this these contacts that give you that light switch effect. It's no longer an on-off switch like we talked about earlier, or a human has to interface with it. You can remotely, some way, shape, or form, through software or whatever, energize this relay and cause these contacts to close so that you can take another electrical value that's waiting here and transport it out. Transport it out this pin to the object you want to control. Relay is, the basic, for basic conversation. When they tried to name this product, I'd imagine 100 or so years ago, it's like handing off from someone to someone. Well, here we're using very little energy to energize the coil, to create the magnetic field, to suck down the mechanical linkage, that closes our contact. Getting the right angle here. With it closed, you have the ability to transport maybe a different voltage. Although I don't like mixing voltage inside relays. I asked the question years ago to a lot of professional minds. Couldn't get a straight answer. But I have seen scenarios where the coil of a relay could be energized with a DC voltage, and it is transporting an AC voltage out the high current side. We want to call this the high current side of the relay because normally relays are energized by very little current flow, but they are transporting higher energy devices, current drawing, higher wattage equipment by way of their contacts. So this pin right here is the common, because it does nothing. It just sits there and waits to get interacted with. This is the normally open. The state of how relays are when you name the contacts. This is a normally open set of contacts because in its de-energized state, that's what it is. It's normally open. That's how we talk about normally open and normally closed relays. So these are kind of difficult to open, but you can figure it out if you like. There's several that you just got to stare at them. This one happened to be tabbed. Let me see if I can get this right. That was in like that. Oh, well, wait a minute. I'm going to energize it. So we're going to give ourselves a 12-volt DC signal. Now, some of these relays, the low current side, will have a diode bridged across here. So when you see a diode integrated into the coil side of a relay and not the contact side, when you see it integrated into the coil side, that means that they have to be connected up in the correct polarity. That you have to have 12 volts here and ground there. If you hook it up backwards, the coil will not energize, so your mechanical linkages in the relay will not move the contact pieces, parts, and what have you. I don't see a diode on this one, so I'm not going to worry about polarity. I'm just going to hook my red up to here and show you that it is doing its job. I can barely touch it and make it shatter. And there is a significant amount of engineering that goes into a relay and all the little metal parts. Just take note that the contacts themselves are of a different metallic characteristic. They are literally made of a different material that's dropped into this flat copper bar and riveted over. It's smashed, flattened out. So this, on this common here, it's a little itty bitty contact that's dropped into a pre-drilled hole, and then another machine comes down and flattens it out. This is what people mean when they say they have a relay that has dirty contacts, or an older vehicle, a set of points. The repetitive smacking into one another creates wear and tear on the contacts, and the way you can fix that is you can fish in a piece of sandpaper and rake it back and forth and clean the contacts. So that's a very basic relay. There's an automotive relay made much differently, but now that we use the information we have from this one, we can start to make a few assumptions. But this one takes a little bit more staring at to try to figure out where is the coil, unless you happen to know the numbering system on the bottom of the relay. I'm not going to go over that, but I'll just say to you that I've pretty much got it memorized. But what I'm hunting down is the coil. That must be my coil. Let me work this by hand here to see what's moving. Where's the moving junk at? Oh, I found it. So then there must be an iron core, and sure enough, there's the iron core. This must be the coil. This piece here must be the part that gets sucked down. And then if I travel over to here, I can see what appears to be a set of contacts going on. So then I can find, oops, sorry about that, guys. I can see that there's a little thin wire right here. Right there. That's soldered to that tab. So that must be one side of my coil. And then, based on experience, I can assume on the other side of the coil, I'm going to have a similar little tiny wire somewhere. And sure enough, right here is a tiny little wire. Right there. Associated to that tab, which is associated to this. So that must mean my my coil is right here. And when that coil is energized, I have, apparently, if I trace, let me keep my fingers on the coil when I energize it in a second, I can see this little, this is the guy here that's switching, but I notice that the flat bar is always making contact over here with this. I'm moving it by hand. So in this case, this relay has two sets of contacts. that are, one is normally closed. There's your normally closed contacts right there. Sorry about that. Tiny work. So this must be my common, which happens to be the guy that's moving. So earlier I said the common usually stays stationary. In this case, the common is not stationary. It's the guy selecting between the normally closed set, and then when it's energized, the normally open guy over here is associated to the common. So then that must mean I can trace this contact out for the metal, and I could dissect this and see that the metal work for the normally open side to the left travels straight down and pokey outs and comes over here. This must be my normally open, and I'd have to tone it out to find the normally closed and common, but 87 and 87A and 30. 30 is normally the common, then you got 87A or 87. So these are my contacts, and that's my common for the contacts. But the coil is going to be electrically isolated from the contacts. So if we energize this guy with some DC power, and I see a resistor in there, deep in there. Let's see if you guys can. Oops. Way down in there, there's a resistor. Barely make it out. A few stripes on it. Looks like the first band is brown, but I might be wrong on that. So we energize the coil, and we'll watch this guy right here when I bring the ground over, because we've already determined that tab is the coil, because that little tiny hair. And we'll watch it switch. And notice the heavy-duty engineering going on here. You have a real excuse me. You have a pretty heavy-duty little spring right here. Feels pretty tense too. My stomach's growling. I apologize if that's coming through on the video. Yeah, so that's a relay. Again, relays are generally larger in the world of electronics, because we started out with things like switches, on-off switches, just regular blade switches, like on your wall. And then we invented things like vacuum tubes, which vacuum tubes, if you go down this rabbit hole, you'll find out these things do pretty darn much everything our most complicated electronics and software do to this very day, to include photo optics. You can just Google some old U.S. Army training films on vacuum tubes, and I have about 100-year-old record player that uses what Philco says is beam of light technology. It uses light to communicate across an air gap to pick what song to play on a record based on a button that is pushed on the front. And this is a very old Philco radio made in the engineering was going on in the 1930s for this radio. So vacuum tubes, switches and vacuum tubes were pretty much the high-tech stuff of yesteryear, to include solenoids. This is a solenoid that would energize. There's a coil in there, and the specifications say that it is 120 volts necessary to operate it. And well, I can give it 120 volts and we can hear it click if you like. Generally speaking, well, nearly all the time, AC voltage is not polarity sensitive. You hear that doing at the end? That's an awful loud solenoid. But the job this solenoid is doing, this came out of a washing machine. Let's just double check something, because I could probably mark one solenoid is bad and one is good. Could be my AC source too. I might have a situation I'm unaware of. It almost sounds like a motor. All right, so what's happening in a solenoid, in this solenoid's case, is when this solenoid gets energized, I shouldn't really be zoomed in so much anymore, but when this solenoid gets energized, a rod is moving down out of the way, allowing water flow to go from here to there and out to where you need it. It's an electrical device providing control for fluid. It's still a coil, like the coil on a relay. It still has a copper conductor going around in circles. One wire goes in, goes around a few hundred times and comes back out to energize it so that fluid can flow through here and through this hollow tube and out to here. Because right now, if I blow with it de-energized, if I blow in this hole with my mouth or here or here, I can't get airflow. But if I were to energize it, I would be able to get airflow. And I know what this thing did in the washing machine, so, but I saved it because it's a solenoid and I might need that for something one day. Don't know. So we migrated to relays eliminated human interaction. It gave technology the ability to automate things. Here's a 120 volt AC coil, or whoops, sorry guys, 120 volts AC relay. Let's see if I can adjust this a little bit, help prevent that. And we can still see that the fundamentals here about what we just discussed is still the same. We've got a set of contacts. So this must be the common of the contacts, and this must be the normally closed side, and this guy here must be normally open. When it's energized, it should flick to that. And we can locate the coil if we try to examine this real closely. I didn't think to do that before I ran this video to the ONN, or to the ON state. I'm just babbling, hang on. So there's the common right there. The common is tied to the guy in the middle. That black wire. So then, how do we energize the coil? Let me take a look-see at this and hang tight. Let me pause the video. Okay, I'm back. The answer was right in front of my face. I was looking for something to be pre-wired, and in this case, I noticed there was only 3 contacts. So down here we have 2 contacts. 2 contacts right here, which represent the silverish tabs, and we have the common right here, transitions to that black wire and comes around to under here. There's only 3 connections down here. Well, I'm sitting here holding it the whole time earlier. Well, here's my coil right here. Energize the coil and it'll come on. So let me grab some 120 volts. Let me double check and make sure this is the 120 volt one. Yep. And I need some slack. And there's one side. No technical difficulties. Okay. And then powerful loud relay. So yeah, I'm going to give myself a different outlet and see if this is my problem, the buzzing relays. Hang tight. Yeah, so that was not me, or the garage, the fault of the garage. Anytime I hear a relay doing that, that's called 60 hertz hum, which means 60 hertz is newer than the terminology cycles per second, or CPS. Hertz is how many rotations per minute is your power company's source power spinning, 60 hertz or 50 hertz. A lot of times, well, frequency matters. Timing is everything. So this tells me that this relay, I could put a diode across this coil and reduce that clattering. But it seems as though that, well, that would have to be integrated into the circuit for which this is the purpose it's serving. So there's that relay, there's DC and AC relays, but then we changed to get this zoomed out a little bit. We changed to transistors. And that was a battle, because there's a transistor. This is called your collector, and then your I forget which one is which, but emitter or base. Collector, emitter, or base. There's several different varieties of transistors. Here's a little sample thing of NPN transistors, tiny little transistors like this. Okay? There's even smaller ones than these. But what is a relay? A relay is a switch. A switch is a light switch on your wall. A switch is a solenoid. It did electrical work to automate something else, and it changed how do I say this? It has like an evolutionary separation between, you got electricity being used to control water. You know, the two don't normally mix, but if properly engineered, they can work perfectly fine. Solenoids, relays, contactors. Contactors are, geez, just think of something like this on a larger scale, and suddenly everybody wants to call it a contactor. Like on a well pump. The pressure switch on a well pump, or a great big relay. I don't think I have one. Something that takes two hands to lift and carry, where you use 24 volts AC to energize the coil, but on the contact side, 24 volts AC and maybe 1 or 2 amps worth of power to energize the coil, because your contacts are, the work they're doing, they're passing 2000 volts AC, 100 amp. I mean, I'm just exaggerating, but still. The low current side of the relay is usually the coil, and the high current side is your contacts. A relay is a switch. A transistor is a switch. It is a relay. It just, things got smaller and smaller, the evolution of things. We go from vacuum technology to relays. This has a lot of, still has a coil. The coil gets energized by a set of pins. And then you've got two sets of normally open and normally closed contacts. See this? And funny thing is, this is based on a vacuum tube platform. This is a, what do you call it? A Charlie Uniform Sierra 8 vacuum tube. Plugs right into it. The race for how to get smaller, lighter, cheaper to make. Look at all the engineering and technology. Not a lot of mining and holes in the ground requirements to get all the materials to make this. I mean, you've got your Bakelite material, you got glass, which is sand, you've got various wire in there that are doped with different things on the periodic table to make them withstand the heat. Things got tinier in manufacturing. Things got tinier in the world of switching. And you have a transistor technology. We call it TTL technology. And then all of a sudden you get to a point where you're at a circuit chip and there's about 40 billion of these right here inside that little tiny glass. And you can see the legs coming off of this. I wish that camera would focus. Lots of reflection. All the little runs coming off of that one chip. Right inside there. And a transistor is nothing more than a hybrid of a relay and a switch. Let me see if I can zoom back a little bit. Nope, I've gone as good as I can go. So let me just scoot stuff out the way. And I'll just draft up a basic transistor here. And let's do the schematic symbol. We will come in and we will go, let's say, collector, emitter, and base. And they say technically a transistor is nothing more than two back-to-back diodes. We'll make ourselves a common emitter NPN, a common emitter NPN, common emitter not pointed in, so that means you have a diode here that is not pointed inward, it's pointed outward, so that makes it NPN. If this diode symbol were flipped around to where it was pointed that way, it would be a PNP. Pointed in, not pointed in is NPN. PNP is pointed in, and you just forget about that. This is a switch, this is a relay, because what you do is you use a tiny voltage here to control a large voltage here. A small voltage, large voltage. And this is called the trigger. You would trigger the base with a tiny static voltage of, let's say, 5 volt. It could be, well, actually, let's just trigger it. Let's just trigger it with 1 volt. And let's say you have 40 volt here. So how this works is, if you send in little tiny bits of static voltage to the base, that will create the field requirement like in a coil. And all you really hardcore electronics guys are going to really bust my balls, but this is teaching to the newbie. A low current value is energizing the coil so that we can deliver high current hard working voltage through the contacts. The contacts never are electrically tied to the coil. Not necessarily always true, but I don't want to go down that rabbit hole. Now we got a static voltage, and this is called the, in a transistor, it's called the depletion region, which is, think of it as a air gap of material that you have N charged, P charged, and N charged, and nothing can get through until you have an external influence right there. You have to have an influence. You have to throw a little bit of moisture on it or condensation in here. And this depletion region allows current flow to pass through if there's a static input. So now we've created a 1 volt static input to the base. We can now transport our 40 volts through the transistor just like this. And it can go out and be power delivery to a device to do some work. TTL technology. TTL, transistor to transistor logic. It's getting to, it'll be a while before it's antiquated, but it is very old technology. TTL has been around for decades. It got us to here, where the circuit, this circuit chip is only as big as it is because I'm a human. I have hands. I have to handle this darn thing. The real happenings going on inside this chip is really just in a couple of 3, 4. Well, I wish you guys could really see what's happening in there. But you can see individual little runs coming off of that chip in there. There are the schematic for this, if you needed to print it out, would be like 100 foot by 50 foot, so that the human can interface with it and trace it, mark on it, and troubleshoot it. This is the power of silicon. All right, guys. Way too long of a video, but what is a relay? It's just a switch. So is a transistor. It's a relay, which is a switch. And so is that. It's a switch. See ya. And thanks for watching, and have a great day. And don't forget, reject the New World Order and the pedophiles. See ya.